Yeah, so this is a joint work with Will Ma, who's actually in the audience today, and Pranav and Nuti. I don't believe he's here, unfortunately. Okay. Good. So yes, the focus of the work is on online contention resolution. Before I actually get into this, I want to get motivated with a problem that we just actually heard about. So instead of the single item kind of profit inequality, I want to focus on something called the profit inequality matching problem. So it's the same kind of setup, except now my input is going to be a general graph with known distributions describing its edge weights. And so this is done via the product distribution, meaning that the weight of every edge is drawn from the known distribution and its independent instantiations. So the goal of the problem is I want to output a matching large expected weight. And the reason the problem is interesting is that initially the weights are unknown to me. So instead, they're going to be revealed in some sort of adversarial order. And each time I see an edge, I have to make an irrevocable decision as to whether or not I want to match it. You can imagine this process continues. I take the edge AB, I learn the next edge, I pass on it because I have to, and so on and so forth. Eventually, I take edge 5, and the output of my matching is now these two green edges. So the goal is the same as in the single item profit inequality case, except now I'm going to compete against the expected weight of an optimum matching of G. Good. So the profit secretary matching problem is similar, except it's slightly easier for the algorithm in that we get to randomize over the arrival groups. And finally, the one other variant of the problem I want to talk about is the profit free order matching problem. So in this case, the algorithm actually now gets to choose the adaptive order in which it sees the edge weights. Okay, so how do you design an algorithm for these types of problems? Well, in all the papers in literature, there's sort of one kind of canonical approach, and it goes as follows. So based on all the distributions which I know, I write out some sort of convex program. And this convex program, you can think of it as upper bounding the benchmark. And so once I have this convex program, I solve it, and what I'm given is then some sort of fractional matching. So the way you can think of this fractional matching is for every edge of my graph, I have some marginal value, and it describes the likelihood that this offline benchmark would take any particular edge. Okay, so then to get an actual algorithm for the problem, the second step is we actually have to round this fractional matching back into an integral matching. And so that's going to be the focus of today's talk, which is exactly this tool called online contention resolution. Okay, so how does the contention resolution scheme work? Well, let's begin with the original definition, which is the offline setup. So the way an offline contention resolution scheme works is that I'm again given some graph together with some fractional matching. And now I'm going to think of every edge as being active with some particular edge value. So it's going to be actually precisely described by this fractional matching. So you can imagine the picture, all these blue edges are active and the red edges are inactive. And now what the contention resolution scheme needs to do is it has to output a matching of only active edges. So the challenge here is that depending on how these edges are instantiated, there may be multiple active edges incident to a particular vertex, and then I won't be able to take both. So in this case, maybe I take the edges AB and CI. So the goal of a contention resolution is to attain a universal rounding guarantee. And it says the following. So if I give you some constant C, then what I want to be the case is that the probability I match any particular edge, given that it's active, is lower bounded by some constant C. And this has to hold over all the edges simultaneously. Okay. So the goal here is to make C as large as possible. And in this work, we're actually going to focus on something called sequential contention resolution schemes. So in the previous sort of picture, as the algorithm, I get to learn the state of every edge initially, and then it's still a challenging problem. But sequential contention resolution schemes are even harder. And the reason is as follows. So you can imagine, initially, I don't know the states of my edges, and I learn them one by one in some order. So in other words, in step T, an edge is presented to me, I learn its identity, and I also learn whether it's active. So if this order phi is generated by an adversary, then we call the contention resolution scheme an online contention resolution scheme. But I can also consider when it's drawn uniformly at random, in which case it's a R-CRS. And finally, I can also consider when I actually get to choose the order of which I process the edges. In this case, we'll call it a free order contention resolution scheme. Okay, so there's many different sort of variants here, but it's a strict sort of inclusion where OCRS is the hardest and free order, or sorry, offline is the easiest.
Just a quick question.
Yeah.
So is there another variant where you actually know the order, but you have to make the decision sequentially? Would you need that? Actually?
Yeah, that's sort of what OCRS kind of is, right? Like it's sort of, but
yeah. Okay, so
yeah.
let's actually wait until.
Yeah, sure. Yeah, this is, sounds good. Yeah. Okay, so quickly, why do we care about these sort of contention resolution schemes? Well, they give sort of lossless reductions to these various profit matching. Okay, so if you give me a C selectable OCRS, and I get a C competitive profit matching inequality. Okay, that being said, the applications go beyond profit inequalities. In this talk, I'm not going to focus on this, but there's applications in many sort of just stochastic optimization. Okay, so how sort of works have really focused on attaining the sort of optimal selectability guarantee that you can get for any of these particular settings. So this is the largest sort of C selection guarantee that's attainable depending on which arrival model you're in. The way, so this work today is going to differ is that we're going to put a more restrictive assumption on our inputs. We're going to assume that the edge values of the fractional matching that I'm presented are actually all very small. So they're all going to be upper bounded by some epsilon, where you can think of epsilon as sort of tending to 0. And the reason I'm going to do this is because when we make this assumption, we can get much better guarantees as one might expect. Okay, so in other words, what we're going to do is once we place this assumption on the input, we're going to show that maybe we'll get some selection guarantee C, and as epsilon tends to 0, we actually attain it. Okay. So obviously this seems like a bit of a strange assumption, but I want to argue that it is an important regime. So there's sort of 3 kind of reasons why I think it's an important case. The first is that there's some precedent for why people look at this. And this goes back to stochastic optimization problems in which, because of the inputs people are looking at, the instantiation probabilities are very small. So the best kind of example of this is the stochastic rewards problem. Another sort of application is in the random graphs literature. People care about what happens when I have a sparse random graph with many vertices tending to infinity. So this would be sort of the Poisson regime, where on average I expect to see roughly 1 vertex, or edge rather, per vertex. And what's sort of nice about the results I'll show you is that we generalize these random graphs results to unequal edge probabilities. And finally, and I think this is probably the most important part, is that in many of the previous works on contention resolution, all these sort of hard examples that when people prove negative results are in this sort of vanishing regime. So in other words, I come up with some construction that is very hard to get a good selection guarantee on, and it happens to be the case that it has small edge values. So what this is suggestive is,
do you know the fact that by variable decomposition actually you make the problem instance harder?
Sorry, do you mind repeating this?
So do you know as a fact that by variable decomposition making the random variables smaller, you can actually make the problem harder?
Oh, no. So there isn't like a known reduction. No. So there is in some special settings when you have parallel edges. When you have parallel edges, like a multigraph, for instance, then you can always reduce to this vanishing setting. But if you have a proper graph, then it's not known such a reduction exists.
That's the property inequality of the parallel edges.
Yeah. So I mean, I'll talk this maybe a bit more at the end. Okay, so this is all sort of some motivation for why the vanishing edge probability setting is interesting. And so the focus of this work is identifying what the optimal selection guarantees are for this vanishing regime. Okay, so what are our contributions? Well, the first result is a positive result for OCRS. What we show is that in the adversarial arrival model, we can get a selection guarantee of roughly 382. Okay. How does this compare to the past results? Well, I mean, all the selection guarantees are fairly small, but the original one was just above a third. There was an improvement to about 344. And so this is, I guess, to the second decimal place. But the sort of interesting thing here is we don't actually use this previous OCRS. We actually use a different OCRS to prove this result. How does this compare on the negative end of sides? Well, the nice thing here is that our bounds are quite close. So previously, the best sort of upper bound for vanishing edge values was 4 to 8. And what we do is we consider actually a very simple input. It's just going to be a sequence of trees with all uniform edge values, 1 over n. And what we show is that as n tends to infinity, and you look at a very large tree, then you can't beat 0.393. So there's a very small gap now in terms of where the optimal selection guarantee is for OCRS. And what's kind of more interesting actually is that, okay, so if we look at this sequence of trees and we make a assumption on my OCRS, so I tell you that the matching it outputs is roughly the size, or it's concentrated around its expectation, then we can prove the exact sort of upper bound of 382. And so that I claim this is sort of a natural assumption, mainly every sort of OCRS people actually analyze in the literature does have this concentration property. So in that sense, there's very strong evidence that 382 is the exact selection guarantee here. Good. Finally, we also prove one other unconditional result where by modifying this tree and adding in these small cycles, we can get a slightly better upper bound. Good. What else do we prove? Well, the other two results are in the random order and free order setting. So in these settings, it's actually easier to think about the algorithms as being executed on something called one regular inputs. So an input's going to be one regular if for every vertex, if I sum up the edge values, then I get 1. And so it's been shown in the literature that this is sort of without loss. And I think this is very believable, right? So the hardest inputs are always going to be when I have sort of the most expected number of active edges per vertex. And then the nice thing about once we reduce to this setting is that the algorithms are very simple. So for instance, in the random order setting, if you just greedily process the edges, then you get a half selectable RCRS. And this is actually best possible. So there's a corresponding negative result that says even in the vanishing regime, you can never beat a half. So this, together these two results then say that the half is the right answer in the random order setting. Our final result is a free order result that says if you take a non-uniform random order and greedily process the edges, then you can slightly beat a half. And this is quite interesting because combined with this half upper bound, it actually says that the free order setting is strictly easier. Good. Okay, how am I for time?
No, 4 minutes.
Okay, sure. So I'm just going to focus on some of the techniques of the OCRS, just the positive result, and due to time, I might skip some of the details here. But the way the past sort of results work is it's based on this recursive style analysis, where when an edge arrives, you check if its endpoints are unmatched, and the edge is active, and if it is, then you flip a coin with a certain probability and add it to the match. And so to prove that this sort of OCRS is well defined, one has to upper bound the probability C by the probability that the endpoints are unmatched. It's quite easy to see that if I'm actually executing on a tree, then the matching status of U and V are going to be independent. And so what I can do is I can actually get this 0.382 guarantee very easily. On the other hand, there's a previous work that also looks at the vanishing regime for contention resolution. And the main sort of takeaway of this paper by Pranav and Jan is that if I'm in the vanishing regime and I restrict my graph to the active edges, then if I look at an edge, it looks very tree-like. So it seems natural that because of these two things hold, I should be able to prove that this previous OCRS also gets this 382 guarantee for vanishing edge values. I won't go into this so much, but unfortunately, because of this recursive nature, it's actually quite difficult to prove this, and we're not actually sure this is true. So instead, we have a different approach for proving our positive result, and it goes as follows. So let's call an edge locally tree-like, provided if I look to distance L from any from the endpoints of a particular edge E, then I don't see any cycles. Okay. So for instance, if the graph is girth G, then every edge is going to be roughly G over 2 locally tree-like. The way we prove our positive result is a two-step approach. So the first step is we design an OCRS that does very well on locally tree-like graphs. So in other words, if you guarantee me that an edge looks tree-like up to a decent distance, then the selection guarantee is very close to this 382. So this is the step one of the proof. And what's interesting here is we prove this for any fractional edge. The second step is a sort of a black box reduction, where we show that, okay, if you give me an algorithm that works as in step one, I can use it in a black box manner to design an algorithm for the vanishing edge value regime. Okay, so let me go over each of these steps briefly. First step is as follows. So you can imagine an edge arrives, and I write down the fractional degree of either endpoint. When the edge arrives and it's active, I check if its endpoints are unmatched, and I accept it with the prescribed probability written. So on trees, I get a exactly 382 selectable OCRS. And what we show is that, okay, if I have a locally tree-like input, then the same kind of guarantee holds. So as L tends to infinity, these marginals cancel out, and I get a guarantee tending to alpha as L tends to infinity. So this is based on it's called a correlation decay analysis, where because the graph is locally tree-like, the matching status of any two vertices is not influenced by each other. The second step, and I think the second step is actually the more interesting step, is as follows. So it's going to be this black box reduction that I'll describe in the offline setting first. So you can imagine I know all my edge states in advance, and what I want to do is the following. So I have my offline contention resolution scheme, and I want to use it to then design a vanishing edge probability contention resolution scheme. So the way this works, and we prove this reduction, is inspired by something called the sprinkling method in random graphs literature. And it works as follows. So you can imagine that all my edge values are upper bounded by some epsilon. And now I set L to be the locally tree-like input that I desire. So this is going to be tending to infinity because epsilon's tending to 0. And now what I do is I draw a random subgraph. And it's going to have the property that for any edge, it's typically L locally tree-like. So if I write down the probability, any edge joins this random subgraph, then I can argue that if I normalize these original and marginal values by the y values, I still have a fractional matching. And so if I now run my original OCRS on this new fractional matching, then I can show that the probability I end up matching a particular edge ends up being exactly what I want. And as L tends to infinity, I recover the 382 guarantee. Okay, so this is quite quick, and I think I'm out of time. So I'm just going to end with 2 open problems, and I can take questions maybe offline. So basically, one thing we'd like to do is get rid of this technical assumption on concentration. And the second thing, and I think Rod, you mentioned this, is we'd like to actually understand if there is this sort of black box reduction. Yeah. Okay, thank you for listening.
All right.